All right, let's go ahead and get started. I want to welcome you to Unit 7 now. This is chemical reactions, and we want to talk about how chemicals come together to form products, right? And to do that, we're going to need to know a few of the indicators of a chemical reaction. What are some things that are not necessarily diagnostic, but clue us into the fact that a chemical reaction is in the process of occurring or has occurred? Well, the first thing is a change in temperature. Now, you got to be a little bit careful with this one because of the fact that just because there's a temperature change doesn't necessarily mean that there's been a chemical reaction. For example, if you place your hands next to a campfire, your hands are going to warm. But that's not a chemical reaction. And likewise, if you open a refrigerator door and you feel a cold blast of air hit you in the face, that's not a chemical reaction either. So chemical changes or chemical reactions produce changes in temperature, but it's not diagnostic, right? It's not diagnostic. In other words, if you see a change in temperature or feel a change in temperature, it doesn't necessarily mean that a chemical reaction has occurred, but it's an indicator. The next is the production of gas bubbles. Another one you have to be really careful with because of the fact that, and I put an asterisk here, the bubbles must contain a gas which previously did not exist. A new substance is the key here in order for it to be a reliable indicator of a chemical reaction occurring. For example, if I boil water, the bubbles produced in the boiled water, and we've all seen this when we're making spaghetti or boiling eggs for tuna fish salad or whatever the case may be, you see those little bubbles. Now, does that indicate that when water goes from a liquid phase to a gas phase, that those bubbles indicate a chemical reaction? The answer is no, because of the fact that the bubbles produced have in them not a new substance, but instead water vapor, gaseous water in the gas form. So this is not a chemical reaction. So be careful with this one as well. It's indicative, but not diagnostic. Let's take a look at number 3, the formation of a precipitate. What do we mean by a precipitate? Well, if I put two liquids together, and I notice that when I put them together that a solid forms in the bottom of the test tube. Let's say I put them in a test tube. A solid falls to the bottom of the test tube. That solid did not exist before. That's a new substance, and we call it a precipitate. If you see a precipitate, that's an indicator that a chemical change has occurred. And finally, color change. If, for example, you're on a bicycle tour or trip in Vermont in, say, November or October, September, October, November, any of those months, you're going to notice something very peculiar about the foliage, the trees. The leaves are going to change color. They're going to go from a summer green to a fall red, orange, yellow, those types of fall colors in the leaves. Why does that happen? Well, it happens because of the fact that there's a chemical change or a chemical reaction occurring in the leaves themselves, right? So if you see a color change, that's an indication or an indicator that a chemical reaction has occurred or is in the process of occurring. But let's take a look at the one that is absolutely the most diagnostic, the most important one, and that is the formation of a new substance. When something comes into being that was not present before, then that new substance is absolutely diagnostic of a chemical reaction. That's a chemical reaction, okay? So that's it, the indicators for a chemical reaction. So a chemical reaction represents with symbols and subscripts, and we'll talk about what subscripts mean in just a moment, the relative amount of reactants and products, right? So reactants form products. Bonds between atoms and molecules are made and broken in this process. So that's what a chemical reaction means. Remember what Dalton said. John Dalton said that matter can't be created and it can't be destroyed, but the atoms can be rearranged. And that's really what we're talking about when we talk about a chemical reaction, the rearrangement of these atoms. Reactants become products. Sometimes heat is required. We call that an endothermic reaction, but we'll worry about that later. And sometimes it is a product. Sometimes the heat is the product of the reaction. We call that exothermic. Now, an arrow represents the transformation of reactants to products. An arrow represents going from reactants to products. Coefficients specify the relative amount of reactants and products. So let's go from abstract to concrete. Let's take a look at our very first chemical reaction. And here it is. We have H2, that's hydrogen gas. That means it's diatomic. H2 means it's diatomic. Di means 2. There's 2 atoms involved in that H2 gas. Plus O2, that's oxygen gas, and it's diatomic as well. Yields, that's what that arrow means. We've got reactants on the left, products on the right. H2O, water, H2O. Now, notice in front of the H2, on the left side, on the reactant side, that there is a 2. What does that mean? Well, it means that it's going to require twice as much of the H2 as the O2. Now, there's no coefficient in front of the O2, so we'll assume it to be 1. So it's going to require twice as much hydrogen gas as oxygen gas to form 2 parts of H2. So let's read the reaction like we're from left to right, like we would be reading a sentence in a book. We have 2 parts of hydrogen plus 1 part of oxygen gas yields 2 parts of H2O. Now I'm saying parts because the fact that it's kind of like a recipe, right? If you are making, I don't know, some kind of cake, right? You need so much sugar and so much flour and so much milk and so many eggs and so forth, but you have to know what parts. You have to know how much, and that's what these coefficients tell us. Folks, later on in a couple of more units, we're going to be talking about something called the mold. So I'll replace the word parts, right? Or, yeah, parts with the word mold, but we won't worry about that right now. All right, so here we go. The plus sign then again means reacts with, right? The plus sign means reacts with. The arrow means produces. So we have H2 reacts with O2 to produce 2H2O, right? Now, if you see AQ in parentheses, that indicates dissolved in water. AQ means dissolved in water. S means solid for obvious reasons. L means liquid. And G means gas, in parentheses, right? All right, so we want to talk now about 5 basic types of chemical reactions. There are literally thousands and thousands of them, but we want to categorize them. We want to talk about basic types, 5 basic types of chemical reactions. The first one we'll talk about is synthesis. What do we mean by synthesis? Well, it's the combination of 2 or more substances to form a compound. So if we have kind of in a generic way, A and B. If we put them together, we're going to form AB, right? We're just going to put them together. I mean, I don't mean to sound overly simplistic, but that's what it is. You take A, some substance, and you take B, another substance, you put them together, and you get AB. It's just that simple. So let's take an example now. Let's take a concrete example. And we've had our unit on nomenclature now, so I'm going to name these with the proper name. We have CaO, that's calcium oxide, right? Calcium oxide plus dihydrogen monoxide. You might say, why didn't you say water? Well, I'm concentrating on nomenclature now. Dihydrogen monoxide, that's what I'll call the water. Yields, that's what the arrow means. Calcium, I've got a polyatomic ion. Let me look it up. It's hydroxide. Calcium hydroxide. Calcium oxide plus dihydrogen monoxide yields calcium hydroxide. All right? That would be a synthesis reaction, taking 2 things, put them together, and form one thing. All right? Okay. We've got next, decomposition. What's decomposition? Well, it's the opposite. It's the opposite of synthesis. Taking 2 things together and taking two things that are together and pulling them apart, that's decomposition. A compound breaks down into 2 or more simpler substances. Notice it could be more than 2, right? So let's take AB. Some substance, AB. We break it down into A and B. That's decomposition. That's not hard. Let's take an example. We've got water. I'll just call it water this time. Water, H2O, obviously a liquid, 2 parts of it, breaking down into 2 parts of H2 gas plus O2 gas. All right? This, by the way, is called electrolysis. When water breaks down into hydrogen and oxygen, the process is known as electrolysis. That's a chemical change because new substances are formed, right? H2 and O2 were not there before, were they? No. So a new substance is formed, so that's a chemical reaction, right? That's a chemical reaction. So that's 2, synthesis and decomposition. Let's keep going. Here we go. The third one is called single replacement. I'm just going to give a kind of a brief introduction to single replacement because there's actually quite a bit to it, but I wanted to start at least here, and then we'll go on later on. It says see notes on how to interpret the activity series chart on page 5. So once we get to page 5, you'll know how to interpret something called an activity series. But let's just get the basics here. It says single replacement reactions. A metallic element replaces the cation, a metal of a compound, right? So what you can have is you can have a metal in a metal element in a single metal, and it can replace the metal in a compound, right? Sometimes, maybe. It doesn't always happen, and that's what we'll learn about when we get to page 5, that it doesn't always happen. Sometimes you put a metal with a compound and nothing happens. But in this case, let's take a look at what happened. We had A plus BC yields AB plus C. What happened? Well, what happened was that apparently A replaced C. You see that? A replaced C, just like that. And when A replaces C, then what you're going to have is a single replacement reaction. Now notice C is by itself now, right? C is by itself. So the free element must be more active than the element being replaced. We're going to check that activity series later on. That might not make much sense right now when I say the free element must be more active. Well, what's more active? What do you mean more active? We'll talk about that. Be patient. Wait till we get to page 5 and I'll teach you about the activity series. But I just want to give you the basics of single replacement reactions for right now. All right. I want to give an important note to you pre-AP students out there. All right, here we go. Nonmetals can replace nonmetals. All right, so metals can replace metals, but nonmetals can also replace nonmetals. Now, here's what you need to know. Reactivity increases as you move down a family or group. So, for example, fluorine will replace chlorine because fluorine is higher on the periodic table than is chlorine, but not vice versa. It won't work the other way. Again, be patient. See pages 5 and 6 for a better explanation of using the activity series chart and a nonmetal replacing a nonmetal. So just be patient, okay? We'll get to it. But I just want you to know what a single replacement looks like. A plus BC, something gets replaced, AB plus C. All right, so that's single replacement. Let's talk about double replacement now. So here's a double replacement reaction. Ions of two ionic compounds exchange partners. Okay? So, generically, AB, that's a chemical compound, an ionically bonded compound, plus CD, another compound, yields AD plus CV. Now look what happened. A switched with, is now together with D. C is now together with B. There was a double replacement, right? A switching, right? Just like that. One product must be insoluble or there will be no reaction. That's critical. One of these two products, AD or CB, has to be a solid, right? Remember I said that a precipitate is the product of adding two liquids together and forming a solid? Well, here it is right here. One of these has to be insoluble, it has to be a precipitate, or you get nothing. Check the solubility table to determine if a precipitate forms. Again, be patient. This will come to you on pages 6 and 7 of these notes, right? It'll come to you a little bit later. Let's take a look at a specific example. Lead nitrate, that's aqueous, plus 2 parts potassium iodide, aqueous, yields lead iodide, solid, that's their precipitate right there, it's going to go, plus 2 NO2 gas. That's double replacement. Let's finish this up with combustion. In combustion, you're always going to have the same thing. You're going to have, and this is a burning of a hydrocarbon. In this case, I've got C2H or CXHY, right, plus O2. Some hydrocarbon yields CO2 and H2O. And here's my example. We have methane plus 2 parts of oxygen gas yields CO2 gas and water. Notice I always have the same products, right? Always have the same products. Folks, that'll do it for this one. I'll see you in the next one. Thanks. Bye.